My name is John Mulcahy. I know I had a chance to get to know a lot of you earlier this year when I served as one of Carnegie's co-interim presidents. Tonight I'm back representing Carnegie as the director of the observatories, which is our astronomy branch located in Pasadena, California. As many of you know, we have a new president at Carnegie, Eric Isaacs, but Eric is on his way to Europe now, where there's a big celebration for our founder, Andrew Carnegie, that's being held at the Carnegie Peace Palace at The Hague. So unfortunately, he's not there, but that means I get to be here today. And this is a particularly interesting topic for me because this is one that my department was very involved in, as you'll hear more about. So I'm sure a lot of you, if you think back a year ago, at least if you're an astronomer, you think about to last August. Last August was a very special month in astronomy. As many of you know, I'm sure many of you participated, there was, of course, the big event which was supposed to be the celestial event of the decade, and that was the big total solar eclipse, the Great American Eclipse as it became known. And myself and pretty much every astronomer I know was headed somewhere to see totality for that eclipse, the first many of us got to see. That event happened on August 21st, you might remember, of last year. Very few of us knew, and none of us knew, of course, that the universe might have a bigger surprise for us. And in fact, the universe sent us even a bigger present, so to speak, and that was on August 17th, and that's the topic of tonight's talk. It was on that date that there was a LIGO detection, and we're going to hear about LIGO. Some of you were here for the lecture in June. You heard about LIGO. Gravitational wave event, and less than 11 hours after that event, optical light from the merger of two neutron stars was witnessed for the very first time. And tonight you're going to hear from three of the individuals, all Carnegie folks at the time, who were involved in that discovery. It's really quite remarkable. These were the first humans in history to see the light from two neutron stars colliding with each other. And that's pretty fascinating. So we're going to have a short presentation tonight about kind of this event and how it went down from our first speaker, who's Dr. Tony Piro. And then afterwards, we're going to have a panel discussion. I'm going to ask some questions, and I know at some point we'll have a chance for you folks to ask some questions. But let me turn over to Tony and tell you a little bit about our speaker tonight. One of our newest initiatives at the Carnegie Observatories in Pasadena has been the development of a theory program. And in fact, Tony is the latest hire in this field. He's what we call a theoretical astrophysicist. What this means is that he aims to understand the physical mechanisms underlying the observations that the astronomers like myself take at the telescopes. And also to predict things that we have yet to see. And it's a really fascinating and important new field. Tony is an expert in many things. Among them, I had to write them down, there were so many. General relativity, nuclear physics, thermodynamics, condensed matter physics, and fluid and magnetohydrodynamics. Needless to say, he's a pretty smart guy. And he uses this impressive array of knowledge to address some of the most fundamental questions we're trying to understand in astrophysics. His specialty is really understanding what I like to think, things that explode, explosions of all sorts in stars, which is what we're going to hear about today. So Tony received his PhD from the University of Santa Barbara, and then he was then a postdoc, first at UC Berkeley and then Caltech. After that, he came to Carnegie as a postdoc. He was then appointed our second George Ellery Hale Distinguished Scholar in Theoretical Astrophysics, and last year he became a staff scientist at the observatories. I think after you hear Tony's remarks tonight, you're going to understand why we are so excited that he was able to join us here at Carnegie. So help welcome Tony Piro to the stage.
All right, let's see. Great, so thank you for inviting me to talk about our exciting discovery from last fall. So I'm just going to jump right into it. Like any good story in physics, this one begins with Albert Einstein. And this is actually Albert Einstein in our library in Pasadena in 1931. And you can come still visit this library today in Pasadena. And so in 1915, Albert Einstein published his theory of general relativity. And it represented a completely new way about thinking about gravity. So before, from the time of Isaac Newton, gravity was thought of as an invisible force between any two bodies that would attract them together. But instead, in general relativity, Einstein told us that gravity is actually the warping of space-time by mass and energy. So what does that even mean? So one way to think about that is space-time is like a rubber sheet, and masses like the Earth are bowling balls that warp that space-time, okay? And so the moon goes around the Earth, not because there's some invisible force that's attracting it, but because it's trying to move in straight lines through this curved space-time. Now, if that wasn't amazing enough, there was other implications of this theory of general relativity. And one of them, which Einstein worked out just a year later in 1916, was the idea of gravitational waves. And the idea was if you had two massive bodies, like two black holes, let's say, orbiting around each other, it would act just like if you were moving your hand around in a pond, and which would send out waves of water, right? And in the same way, these masses moving around send out waves, but these are actually ripples in space-time, okay? So these are ripples such that if this wave came by you, lengths would actually shrink and grow. If you had a clock, it would speed up and slow down as these waves were passing by. So how would you detect these amazing gravitational waves? Well, we actually have 3 gravitational wave detectors now. 2 are in the United States. These are called LIGO. One's in Washington and one's in Louisiana. And there's another one in Italy called Virgo. And these arms here are about 4 kilometers long, and we have lasers bouncing back and forth along these arms to measure the distances extremely accurately, and in this way actually be able to detect the presence from gravitational waves coming across the universe. And so on September 14, 2015, gravitational waves were detected by the 2 LIGO detectors for the first time. You can see, even though these 2 detectors were 2,000 miles away, you can see this is as a function of time. These wiggles represent the shrinking and growing of these arms as the gravitational waves were coming past. You had the same wiggles at both sites, okay? And so you might ask, what kind of black holes were these that these gravitational waves were detected from? And so what's amazing about these gravitational waves is the frequencies of these, around 10 to 1,000 hertz, are in the same range of frequencies that we actually hear with our ears. And so actually together we can detect gravitational waves and figure out what mass these black holes were. So would you guys like to try to do that with me? Okay, so the first sound is going to be 2 black holes around the mass of our sun merging together. So let's listen to what that sounds like. So all right, so maybe we'll come back to that then. All right, so here again, these are the 2 gravitational wave detections. And I'll just tell you that these were both black holes around 30 times the mass of our sun, okay? So amazing detection. And that wasn't all. So in the years since, LIGOs and Virgo have actually now seen 6 merging black holes. And because of this amazing discovery, they were awarded the Nobel Prize in Physics in 2017. An amazing accomplishment. But was there more left to do? Yes. The next frontier was merging neutron stars. Okay, so what's a neutron star? So neutron stars are the cores of massive stars after they die. So stars about 10 times the mass of our sun or larger, they'll have explosions when they die, and they'll leave these remnants called neutron stars. And these neutron stars are amazing objects. So a neutron star weighs about 1.5 times our sun, but it has a radius of about 12 kilometers, about the size of a city. Okay? These are incredibly dense objects. If you took 1 cubic centimeter, 1 sugar cube of a neutron star, it would have the mass of all the humans on Earth packed together. okay? But these are the kind of extreme objects we need circling each other to make gravitational waves. And these aren't just fictitious. We know about thousands of these in our galaxy from all stars that have been dying over the history of our galaxy. And the last thing to know about neutron stars is they're actually way better than black holes. So black holes have great PR. Everyone wants to ask about black holes. But the difference is neutron stars actually have material. They're not just holes in space-time. And so what that means, as the neutron stars are merging together, they start ripping each other apart tidally. And this flinging of matter potentially is something we could actually observe with our telescopes, whereas black holes are black. Okay? And so what happened is groups of astronomers like ourselves had these agreements with LIGO and Virgo, where we get these messages on different things they were detecting. And the astronomers would then be able to follow up those detections and see if any light was being created. And usually it'd be a message about two black holes, some boring black holes merging together. And we had observed it because we were good scientists, and we wanted to make sure there wasn't anything there, but we never were able to detect anything from merging black holes. But this all changed on August 17th of last year, when this message came out where it said the candidate is consistent with a neutron star binary coalescence. And so it's a good thing they didn't have me writing these messages, because I would have put way more exclamation points after this message. Okay? So this is an incredible opportunity to actually detect something creating gravitational waves with our telescopes. And so who was this group that was working to detect the light? So there was many people in our group working on this, but I want to highlight some of the key players. So overall, we had, I was the principal investigator of what was called the Swope Supernova Survey. That was the effort at Carnegie to follow up different types of exploding stars. And overall, we had what was called the 1 meter 2 hemisphere group, which was going to be looking both in the northern and southern hemispheres for gravitational wave counterparts. And this was led by Ryan Foley, who's a professor at Santa Cruz. And then his postdoc, Charlie Kilpatrick, and his grad student, Dave Coulter. And then Maria and Ben, who you'll hear more from tonight. And then Josh Simon, who's another staff member like myself at Carnegie. Okay. And so when we got this message, you could imagine we were a little bit surprised. It was hard to believe that something like this was happening. And so here's the text messages between Dave and Ryan, and you can see that Ryan, too, who was on vacation in Europe at the time, was pretty surprised. Okay, stop what you're doing and check your email. I don't have email now. What's up? Neutron star merger at a false alarm rate, 1 in 10,000 years. Coincident neutrinos in GRB. Yeah, I should have picked a more likely thing for a joke. This is literally not a joke. And so, Ryan's playing along. Okay, if it's real, ask Ben to get Spectra, get Swope all night, cycling through the filters. I might leave, but if you're joking and don't tell me now, I will not be amused. I'm not joking, man. Jesus, I wouldn't joke about this. And so once we got over our disbelief, it was time to put together a plan of how we were going to follow this up. And we were incredibly fortunate tonight. So not only did we have the Swope Telescope, where we were doing the Swope Supernova Survey, and we had a Chilean student, Natalie Aloa, working at the telescope for us that night, but we also had people at the Magellan Telescope. So you can see it's a rough business having to work out at this sky every night, right? It's a tough job. And so there's the two 6.5 meter Magellan telescopes, and it just happened that night that both Ben and Josh were working at each of these telescopes. Okay? And so we put together a plan that we were going to split up, covering the sky, the area where LIGO said this gravitational wave source was, so that we could cover the maximum ground and try to find the source as quickly as possible. And so everyone would take images and send them back to Charlie, who would then compare images and try to find if there was anything new in the sky. So the race was on, But this was not going to be easy. Other groups all over the world were going to be fighting to try to find the source first. And we had a huge area to search. The LIGO localization is not as good as you might think. It's not like using a telescope. And so it could actually be in about 100 different galaxies that we have to potentially look through. And we didn't have very much time. The source was right near the horizon. And so as soon as the sun went down, we would only have about an hour and a half to search for it before it ended up setting beyond the horizon and we wouldn't be able to find it anymore. And so we started frantically taking images of the sky, looking for this source. And the 9th image that Charlie looked at, in this galaxy 130 million light years away, Charlie found a new source. Charlie had become the first person in the history of humans to see light coming from a gravitational wave source. And so we named the source SSS 17A after the Swope supernova survey, the year 2017. And A, because usually we just follow stuff up. So this was the first thing that we had discovered this year. So the first thing we discovered, but I'd say it was a pretty good thing to discover, right? And so, just like good scientists, we put out a post to that same message board describing that we had a potential optical counterpart discovered by the Swope Telescope of Carnegie Observatories. Here is the name, and here is the location, so that other astronomers all over the world can now follow up the source. But we weren't done at Carnegie Observatories. At this point, we had really just gotten started. And so now we wanted to follow up the event and see how it evolved over the coming days. And so we ended up taking about 3 weeks of data on this event. And it was amazing how all these different astronomers at the Carnegie Observatories came together, helping us take observations, donating some of their telescope time, helping us put different instruments on the telescopes so we could get the data we required. It was really an incredible team effort by a large fraction of the Carnegie astronomers. And so what came out of the fruits of our labor? So we ended up leading 4 papers in the prestigious journal Science, just describing this object. And these papers were led by Dave, Ben, Charlie, and Maria, who were all either students or postdocs at the time, which I was really proud to have the young people leading this effort. In addition, we've been involved in 6 other papers in the Astronomical Journal or Nature about this object. Okay, so needless to say, I'm not going to be able to summarize all of the science in these 10 papers just in the next few minutes, but I just want to give you a flavor of some of the things that we are exploring, and then during the question and answer phase, we can discuss some of the things in more detail. And so one of the first things astronomers like to do is they take the light that's coming from the source and split it into its constituent wavelengths and see how much energy is coming out at different colors, a blue light, red light, green light, which gives us an idea about what's happening, what the material's doing. Okay? And so this was thanks to Josh's quick thinking. After we had discovered the source, he took a spectra. And the spectra that we have are actually the only spectra that anyone had anywhere in the world that night because of his quick thinking. And so what I'm plotting here is the wavelength of light going from blue light to greenish light to red light, going this way to longer wavelengths, and how much light was coming out on this axis. And so you can see here that this is higher on this side, so there's more blue light coming out than the redder light. Okay? And so from this, we can figure out roughly how hot the ejecta was that was getting thrown out from this neutron star merger. And so we measured a temperature, and it was about 11,000 degrees Kelvin, or about, so it was extremely hot at this time. Okay? But that's not all. We didn't just stop right there. Right before the source set, about an hour later, right when it was at the horizon, we took the last spectra we could, right here. And we saw that just in this 1 hour, the source had changed in temperature to 9,500 degrees. Okay? And you think about things in astronomy changing over such long timescales. In just 1 hour, this had changed by 1,500 degrees. Okay? And so what we can do from this is as things expand, as this ejecta is expanding away from the neutron star merger, it cools. Just like if you blow air out of your mouth, you can feel it's cold from the expansion. And so in the same way, the fact that this cooled so quickly in 1 hour, we could actually figure out how quickly that material must be going from the neutron star merger. And so we did that quick calculation, and we found that the ejecta must be moving at 30% the speed of light. Okay? And it was really at that moment we realized this was something incredible that had never been seen before. Okay? And so we continued to watch this object over the next 3 weeks. And it started out bright and blue, like I was showing before, but you can see over the next couple weeks, it turned red. And then it just had this red glow until it just faded away. And so the question is, why did it have this red glow for all these weeks? And so the answer to that question, I'll give you a hint. Is anybody wearing any gold or platinum jewelry in the audience tonight? Yeah? So you're wearing the debris from neutron star mergers right now. And so to set this up, this is the periodic table. And hopefully I'm not causing any post-traumatic stress from high school chemistry classes by showing this. But this periodic table, what we've done is we've color-coded the different elements based on where we think they originate in the universe. And so, for example, you can see hydrogen and helium up here in red. These are basically mostly formed in the Big Bang when the universe was created. Okay? Most of all these different shades of blue have been generated inside of the furnaces of stars or ejected in supernova explosions when the stars explode. And this is this idea, you've probably heard the late Carl Sagan talk about how we're all stardust, right? And this is where that idea comes from, that all this material requires stars to be synthesized. But all this stuff in gold, even though we knew this has to be generated in outer space somewhere, it's been a mystery for almost 70 years where this material comes from. And this is stuff like gold, platinum, uranium, plutonium, lots of rare and expensive stuff. We fundamentally didn't know where it came from in our universe. And one idea that's been around for a long time is maybe these neutron stars could generate this material. And the basic idea is pretty easy to understand. You have a bunch of neutrons flowing out from one of these mergers, right? And these neutrons are all neutrally charged. So unlike protons, where they would want to repel each other, they're able to stick together and form really large nuclei as they're flowing away from this neutron star merger. But these types of nuclei are unstable. So over the coming days, some of these neutrons decay and turn into protons. Okay, there's different types of radioactive reactions that create more protons, and this creates heat. Okay, so there's radioactive heating. So this is a really exciting idea, because what this means is that we can directly measure the amount of heating from this process. We can actually measure how many heavy elements were generated from the neutron star merger. Okay, we just say the more heating that's happened, the more radioactive elements were generated. Okay, and so that's what we did. And so from the red glow seen here, we are able to calculate that about 200,000 times the mass of the Earth was generated in these heavy elements. And this corresponds to roughly 200 Earths just of gold were generated in this. And so from this, we finally learned that sometimes what glitters really is gold. And this ends this large exploration in human history of trying to understand fundamentally where all the elements in our universe come from. We now know the last piece of this puzzle. Neutron star mergers are generating all this material. So what comes next? Well, right now, actually, LIGO is offline. So shortly after this discovery, they took LIGO down so they could upgrade the lasers, upgrade their systems to be more sensitive so they could detect black holes and neutron star mergers at even greater distances. And so that we're hoping that they're going to be back up sometime late winter and start taking data again and be even more sensitive to events like this one. Ourselves, we're preparing now to follow up the next events so that we have everything in place. With the Swope Telescope, we're hoping to potentially eventually roboticize it so that we can, instead of having to have people there, we could just control the telescope remotely and be able to follow up these types of events even more efficiently. And so just to end, this is really a new era in astronomy that is being born. So basically, no matter what kind of instruments we've used in the past, from our eyes to small telescopes, to Mount Wilson in Pasadena, to the Magellan telescopes we have now, we've basically always used photons to study the universe, okay? But now, by combining light and gravitational waves, we have two completely different probes of the universe that will give us more information than any one of the two probes combined. So thank you very much.
We're going to, I don't know, am I on? I can't, yeah, I'm on, awesome. Why don't we have Tony take a seat there? Let me just introduce the other two speakers, then we're going to do our panel discussion, and then there'll be a chance for you all to ask questions. Next up is going to be Maria Drout. So Maria was a Hubble Fellow at Carnegie Observatories at the time. She just started a faculty job this month at University of Toronto, which we're very excited about, a really great place to do astronomy. So that's Maria. And then Ben Shappee, who's our shyest person and doesn't like attention, as you can see. Ben was just finishing. In fact, he was in the last few days of his postdoc at Carnegie when this event happened. And then he's now an assistant professor at the University of Hawaii. So I'll take a seat over here, and we're going to start with some questions. So I think one of the things I always like to start with when we talk about this story, I think people love to hear kind of where you were and how you heard about this. So we saw the text exchange that Ryan Foley had with this student, but kind of Ben, why don't you tell us like where you were, when did you first hear about it?
So I was actually down in Las Campanas, Chile, where the Magellan telescopes are, and I was scheduled to observe on the telescope that night for something completely different than this source. And when you're observing, I don't know, like a teenager, you wake up in the afternoon, late in the afternoon, because you're going to be up all night. And so I woke up and just rolled over late in the afternoon, looked at my phone, and just saw it was littered with emails from collaborators, Tony, Ryan Foley, who was mentioned earlier. And then once we realized what was going on, then Josh and I, who was also Josh Simon, another Carnegie scientist, was down at the telescope too, and we immediately started to arrange just like, okay, we have, we're on both Magellans, which are big telescopes, they're expensive, it's hard to get nights on, and Carnegie has a large share of those, and we also have Swope, so we're in a unique and amazing position to try to find the counterpart to this source. And so then we decided that the three different telescopes would look in different colors to try to find it, because we didn't know what color it was going to be. It was actually quite a surprise that it was blue in the beginning. It was expected to be extremely red right from the beginning. And so we decided that each telescope would take a different color, and we'd look at all the galaxies that we possibly could as fast as we possibly could. And we got I didn't even know how to use the instrument that I ended up using. Because I was going for a completely different instrument, and so then the staff who's there, who are experts on the instruments and how to use them, were stayed up, and they've worked all day, right? They keep the telescopes and get them into proper conditions so we can use them at night. But then after dinner, everybody basically came to the control rooms of the Magellan telescopes to help us to look for exactly what we ended up finding.
Yeah.
Maria, where were you? Or
similarly, I wasn't down in Chile. I was in Pasadena at the Carnegie Observatories at the time, and so I was up during the day. I was not supposed to be observing that night, but I am one of the people who had an agreement with the LIGO Collaboration, so I got the alert in the afternoon. So we started sort of emailing immediately about this and figured out that these observatories in Chile were going to be the first ones that had access to try to find the source, but that it was only going to be for an hour. So sort of frantically that entire afternoon, we were making plans of like, how can we most effectively cover this area, and then got in touch with the people at the telescope, like Ben and others, once they woke up. And so then I was actually Skyped into the telescope Ben was at that night just to help in any way I could, because it's the sort of thing, again, Ben had these nights on the telescope for something totally different. And usually when you have time on a telescope, you've been planning for weeks ahead of time exactly how you're going to spend every minute of the time, because it's very valuable. So then when it all sort of gets thrown up in the air, like a few hours beforehand, you need all hands on deck. So I was Skyped into the telescope, helping with the observations, looking at the data as it came on, helping figure out how to use this instrument we were using, and then processing a lot of the data that came in. So like that early spectra that Tony showed you of the light and how blue it was, some of that was stuff that I pulled down and was looking at that night.
What were you, Tony?
I was in Pasadena as well, and I just remember it being a whirlwind because throughout that whole day we were getting different information. So initially there was a different position on the sky from LIGO, and then it only, at one point, neutrino detectors thought they had seen something as well, and so that was information we were working with. Eventually, they were able to work in that Virgo, which I also showed is the gravitational wave detector in Italy. They actually did not detect it. And that was actually a very useful piece of information because there was only a limited part of the sky where they would not be able to detect it. And so that gave us different regions to look at. So it was just a whirlwind with different changing plans as we were getting prepared for this.
Mm-hmm. Yeah, as I mentioned at the beginning of the introduction, of course, this was 4 days before the big solar eclipse that many of us had trips planned. At Carnegie, we actually did some outreach in some small towns in Idaho, which we had planned to work with some students. I know these guys were going there. And I was in a very remote location in Montana where we didn't have cell phone service at all. And after a while, my assistant finally was able to reach me, and she said, "Oh my gosh, something's going down big. You need to call and find out what's going on." Because it turned out that, as Ben said, things had to change kind of immediately. The instrumentation we had on the telescope was not necessarily the right instrumentation. Particularly, there was an infrared swap. Something had to swap so we could observe this thing in the infrared. And our Chilean crew would not do that without the authority of the director. So it turned out that they were trying to get a hold of me just to say, can we do this? And of course the answer was, well, yes, we should change all of our resources to be able to hit this, because this is really an event of a lifetime sort of event. So why don't you guys, I know you guys were both going, I know you didn't go to the eclipse. You must be you're a theoretical astronomer. You didn't care about that. This is just some random alignment of the sun and the moon. It's not so important. But you guys did go to the eclipse, right? So how did you do that and take all this data for 3 weeks?
It was, let me say, it was one of the most unusual weeks that I have ever been a part of, because it was, not only were we going to the eclipse, which we were, again, going to Idaho, but previous to that, myself, Ben, and another astronomer, we had plans we were driving from Pasadena up to Idaho, and then the week after we were going to be backpacking across state national parks in Utah. That was our plan for that entire week afterwards. And I mean, we ended up not changing our plans to the surprise and consternation of some people like Tony. So what this really turned into, and Ben can tell his side too, but we were literally driving across the country, stopping at national parks, hiking, then like going to McDonald's to get Wi-Fi and download data and try to coordinate all of the observations that were going on for those weeks. I actually at some point downloaded data and was like analyzing it in the tent at night, because we did not stay anywhere. We were just in tents that whole week afterwards. And so it was most bizarre. It was like half a vacation, but really not. So it was a very unusual experience, but one that was a lot of fun because it all worked out. But yeah, it was coordinating things from the back of a car down in Chile. So
yeah. So I had 2 nights on Magellan. So the first night's when we discovered it, and the next night I basically next day I basically didn't sleep at all, because we were coordinating, getting data, and then trying to figure out what we want to do the next night. So then the next night we got as much data as we could as well, which Tony explained the reasons for that. And it wasn't until I was like flying back, from Santiago to Salt Lake City to have Maria and the other astronomer, pick me up on the way to Idaho, that I really finally had a chance to sit down and think about, what we just had discovered. And, then it's like planning, what observations we need. And finally, we got picked up. We went to the school in Idaho. And I remember basically sitting in the school before the eclipse, still working, running out, interacting with students and members of the community from the town for the eclipse, and interacting with this really friendly bunch of people, and then right afterwards running back and just continue working, and then finally running around Utah was entertaining with with tethering to my cell phone for internet, because that's the only internet we could find. But there's only cell phone reception like in the towns in Utah, and so it's like going these long stretches with nothing, queuing up a bunch of emails, get into town, stop, send a bunch of emails, receive them, and then driving to the next town while we're writing more.
And I mean, I think I want to emphasize too how weird this was compared to the way a lot of astronomy works. So a lot of astronomy, like the thing is there in space, it maybe will change on a timescale of millions of years, billions of years, so you can really plan ahead what observations. Okay, yeah. But yes, it's not going to change. So you can really plan ahead what exact observations you want to do. And even, we study explosions, even a normal supernova, which again is one of the most energetic things you can imagine in the universe, even a normal supernova, it will get brighter over a few weeks and fade over months to years afterwards. And we sort of understand that, so you can still plan ahead what you want to do. This, as Tony was telling you, changed so quickly. In the first hour, it had already changed. By the second day, it looked completely different than it had before. And I think theorists actually did a very good job at predicting what this would look like, but we didn't know for sure that that was going to be true. So it was really looking at the data in real time and have to make real-time decisions about what to do the next night, which is very different than the way a lot of astronomy works, where you really can plan ahead. So.
Absolutely. So, Tony, you mentioned that there are thousands of neutron stars in our galaxy. How often do we expect a merger like this?
Yeah, so there are many neutron star binaries in our galaxy that we know about, actually, but none of them are close enough together that they're going to merge anytime soon. It's still going to take hundreds of millions of years for that to happen. But in a given galaxy, every about 10,000 years, it's expected that one of these mergers will happen. So, which is a relatively short amount of time compared to the billions of years that the galaxies have been around.
Especially when you consider that there are thousands or millions of galaxies that we can see across the sky.
Right. So since you're wearing the gold jacket, I'll have to ask you the question about gold. Of course, every time we talk about the neutron stars, I think one of the exciting things,
He's just showing this is his normal fashion.
Yeah, this is. As I said, I'm surprised his wife didn't throw this out.
Yeah.
And so why don't you tell us a little bit about the gold, and we heard a little bit, and Tony said about 200 Earth masses. Well, clearly gold is not very common on Earth, so what does that tell us about these explosions? It must mean that they are pretty rare in general.
Yeah, so what's always been interesting is that when we look at different stars, at meteorites, we always find a lot of these elements, these heavy elements that I've been talking about, in similar ratios to each other. And this has always pointed to a singular origin for most of these elements. And it's always been trying to track down where they come from. So there's been various ideas that people have debated over the last 3 decades or so, mostly between these neutron star mergers and supernovae, the explosions of massive stars, trying to figure out which one's more likely. In the case of the neutron stars, you make quite a bit of this stuff, but they're less often. In the case of the supernovae, they happen about 100 times as often, about once every 100 years, but you make much less of this material. But it looks like the neutron stars are actually winning here.
Do we have an idea about how often we should be able to see these things with the upgraded LIGO? Is there a guess to the number?
So it really depends how normal this event was, but the numbers range from 1 a year to a few a year, up to like 10.
It's still very uncertain, and as Ben said, it really depends how normal this was. I would say actually one of the more interesting things from this was that when we figure out how much heavy elements was created in this, it actually was quite a lot. And enough that if we really have an understanding of how many of these mergers there should be, and if they all make that much or more, it's almost like there's too much of it going on. So it's quite possible that this event was something that actually created more than an average event. And that's what it'll be interesting to see in the future as LIGO detects more of these. And they'll tell us exactly what types of objects are merging together, and we can look and try to find new light from them. And it will look different if less material is created, for example.
Yeah, the other exciting thing is we've talked about black hole mergers and neutron stars merging with other neutron stars, but the next obvious thing is potentially neutron stars merging with black holes, and how that sort of signal will be different. And again, we expect to see light and be able to use our telescopes to study them, but we're not sure how they're going to look differently. So that's another exciting frontier.
So were there any other things, so this is kind of a clue into how heavy elements are made. Are there other things that we learned from this one particular event in terms of physics or astronomy?
So yeah, this event, there were so many different things that were solved with it. It's incredible. So I wasn't able to touch on it very much, but there was also this Gammaray burst that was seen about 2 seconds after. And Gammaray bursts have been known about for like half a century, since the early times when we had satellites up trying to detect whether the Russians were testing nuclear bombs. And we actually found this new class of astronomical objects up in space called Gammaray bursts. And some of those are associated with the deaths of massive stars, but it's been a mystery where those other ones have been associated with. An idea was it was neutron star mergers, but now we directly detected the neutron star merger from gravitational waves, and with our satellites, we saw the Gammaray burst 2 seconds later, solving another mystery. One other thing I could mention is we can actually measure distances in our universe really well with these neutron star mergers. So you saw those wiggles from the gravitational waves. Those wiggles tell us about how much mass is associated with the merger. And then, depending on the distance, then the overall signal gets weaker. And so combining those two pieces of information, how much mass is there and how weak the signal is, we can actually figure out how far these neutron star mergers are happening in our universe, which is really useful for doing things like understanding the expansion history of our universe since the Big Bang. So that's something people are really excited about doing in the future with more of these events.
Because it really is something that, it sounds boring, like, oh, the distance is something, but it really is something that is one of the hardest things to measure in astronomy, is how far away is something actually from you. But it is actually incredibly important if you do want to understand sort of the history of the universe and its expansion. So yeah, it's very exciting.
So for example, there was in 1998, using supernovae as distance indicators, people figured out that the universe was actually accelerating in its expansion. And this is evidence for what we call dark energy, which was this discovery was awarded the Nobel Prize in 2011. And so this is going to enable more of those types of probes of the universe.
So I think one of the other really interesting things about this story was, of course, the timing. But beyond just the eclipse was, if I remember correctly, that LIGO was pretty close to shutting down for the hiatus that they're on now. Can someone remind me how, it was a few days or a week or something?
Yeah, it was something like a week. So it sort of, LIGO had found several more black hole mergers and was sort of winding down. So we thought it was pretty much done. But yeah, the timing was interesting for a couple of points. First, LIGO had turned off just like a week or so later, but also that patch of the sky where it exploded. We mentioned that that chunk was sort of near the horizon in Chile, so it was only visible for maybe an hour, hour and a half at the beginning of the night when it first exploded. But the way it works, it's sort of that chunk is setting lower and lower. So by 3 weeks after the explosion, that chunk of the sky is too close to the sun, so we can't actually view it at night with telescopes. So even if LIGO had stayed on, if it had exploded, again, this is something that actually exploded millions of years ago, and it's taken the light this long to reach us, but if it had exploded 3 weeks later, we would have not been able to see it.
Yeah, so it really was.
Yeah,
Talk about good timing.
Good timing,
yes, in many, many ways. I wanted to we're going to allow the audience to ask some questions. So if people are interested, there's a mic on either side. Feel free to kind of come out and line up, and we'll do that in a minute. But let me ask one more question, which is about Chile. Are there things that are special about the telescopes at Carnegie you think that really allowed kind of the rapid response, so to speak? Since you were down in Chile, you maybe can tell us a little bit about that.
Yeah, so the amount of time and the coordination between the astronomers and the desire to all work together for a single cause, I think that was one of the unique things. So usually when you have a bunch of different telescopes, you have a lot of astronomers from different institutions, and it's very difficult to get astronomers to agree on almost anything, and it's extremely difficult to get them to agree in a short amount of time. And so having Carnegie have a good share of the time on these telescopes really allowed us to then come together and agree that we're going to do this, and we're going to do this the best we can, and get the best observations of the source that we could.
So I'm curious, so those of you, I mean, many of you, of course, have not been an astronomer on the mountain in Chile, but it's a wonderful experience because you get together, you're hanging out with the other astronomers, you have dinner together, you have lunch together. There's all these conversations. It's really a very collegial environment. I'm wondering, of course, this was supposed to be a top secret event, right, at the same time, right? There's restrictions. LIGO really did not allow us to speak about this event. In fact, and it was almost 2 months later before the press release came out.
Yeah.
Of course, it leaked in many ways, including I leaked it myself in Montana because I was so excited. I couldn't help but tell the few people with me, oh my God, the most exciting thing has happened. But I'm wondering, did word spread on the mountain rapidly, or was
Well, there was an exciting event where some of the telescope operators contacted me, and they said, everyone's working very feverishly on this, because it's a lot of work to change the instruments on the end of the telescopes. So a lot of the infrared telescopes, you have to cool them down over a long time before you can actually use the instruments. And they said, is there any bit of information you can get us to help boost morale and see why we should be, working so hard at this? And so what I ended up doing, because this is supposed to be top secret, is I sent them a slideshow that was a hypothetical. If this had happened, this is why it would be so exciting and so important to follow this up. And so the telescope operator went and showed this to all the other people working on the mountain, all the other Chilean workers there. And she said after that, everyone was full steam behind the project.
But yeah, it is interesting because it was something that we had signed all these agreements that LIGO would tell us about things if we kept embargo on it. But part of that was that you have to keep it under embargo amongst people who have signed this, except we really do want the best observations to be taken of this event. So if, for instance, you have access to a telescope, but somebody else who hasn't signed this agreement is observing, you are allowed to tell them as much as possible to get them to take the data for it. And so, as it turns out, because Carnegie, we have this huge collaboration of people who are on many of the telescopes, it did eventually, because pretty soon, I think 80% of the astronomers at Carnegie had observed for us because over those 3 weeks, most of them had had time. So it slowly spread. But I did have a few people who had been on the mountain with me during that time who, afterwards, the press release, they're like, you didn't say anything to me at lunch.
Wow.
And,
So it should also be noted that I was on the mountain for 2 days, but the day crews, the people actually running the telescopes, right? This was a multi-week effort where they're pulling overtime on most days. Mm-hmm. So it's not a small amount of effort for them. So I think that was also a key part of why we were so successful getting these observations.
Absolutely. Well, of course, they're very proud that it was the Chilean telescopes that first saw this event. We have a lot of questions, so this is great. We're going to go back and forth. We'll start here on the left. Go ahead.
Sorry, I can't tell my left from my right.
You're good. Sorry, yeah. You're done.
So you made an assertion earlier that multi-messenger astronomy is very difficult to do on black holes. Would it be theoretically possible to catch a merger involving a black hole with a very large accretion disk, or an active galactic nucleus, or a quasar, or something like that that puts out a lot of radio waves that you could perhaps observe with photons or neutrinos or something?
Yeah, so that's a really good idea. So actually, with one of the previous black hole mergers, there was a gamma ray burst seen at a similar time. And actually, one of the ideas people had was something like you described. Maybe there was some gas around those black holes, and as the black holes were merging, that gas got funneled down and generated some light. Unfortunately, at the end of the day, people decided that it was just a coincidence that the gamma rays were seen near a similar time. But that's a really great idea. For the other types of black holes you're mentioning is the mergers of very massive black holes. So you said AGN. These are black holes at the centers of galaxies like the Milky Way that are millions or billions of solar masses. These can also potentially merge when two galaxies collide together. Now, these black holes are much more massive than the black holes we're talking about, which are more like the masses of our sun. And so LIGO is not sensitive to their mergers, their gravitational waves when those merge. But there's ideas about making a future gravitational wave detector called LISA, which would be in space where the arms would be millions of miles apart from each other. And those types of detectors would actually be able to detect gravitational waves from very massive black holes. So.
Not yet.
Yeah, that's coming.
That's way in the future.
We'll go ahead.
I was wondering when all these heavy elements are produced in the aftermath of the neutron star collisions, they're radioactive and they're emitting a lot of gamma rays. So were you able to take a gamma ray spectrum and to identify each individual radioactive material. Was that possible, or?
That's also a great question. So yeah, as all of these radioactive elements happen, they do. We were not, for this event, able to detect the gamma rays directly from the radioactive decay of this material. And it's a good point that in general with this object, we say these heavy elements were found, and that's from looking at sort of the glow of the light and how it decays put together, and also from the spectrum, but we're not able to detect individual elements from this. And part of that is that this material is thrown out at like 30% the speed of light. So like all of the different signatures that you might expect from individual elements will be blurred together. And also it's very far away to actually see individual gamma rays from that.
So yeah, just to reiterate, it was a little too far away. We have actually seen gamma rays from radioactive material in supernovae that were a little bit closer by. But so hopefully the next event would be even closer, and then maybe we'll see the gamma rays.
Not too close.
Well, that segues perfectly to my question. I thought I heard you say that with the LIGO upgrades, they would be able to detect farther, which I took to mean that they would be able to detect weaker waves, which then I assume means you could detect less energetic events that are closer as well. And I was wondering if you would follow up on those kinds of things and what you might expect to see there. I don't know what the order of magnitude improvement is either, so.
Yes, if there were less massive, as an observer, if LIGO told me there was something extremely nearby, regardless of what it is, I'm going to go after it. So if there was a weaker signal, less massive neutron stars merging, which is unexpected but would be interesting, then we would absolutely go after it.
And similarly with that, yes, you'd be able to detect weaker things closer. And similarly, although LIGO is getting more sensitive so it can find events further away, our telescopes are getting better all the time, but it's not like in this year our telescopes will have gotten significantly better. So also we are considering that sort of these objects that they find that are further away, it will be harder for us to see the same light from them, but we would be able to go after it. Or if there is sort of a weak signal very nearby, it's possible it would create very little in terms of heavy elements, and that would be much fainter for us, but we would still try to find it if we could.
And one of the exciting things about gravitational waves that makes them so weird is if you think about light, when it's far away, the light that you see actually goes down like the distance squared, the flux that you're detecting. But gravitational waves are weird, and the strain that you see of your detectors actually just goes down like the distance. And so that means is if you double the distance that you can detect gravitational waves at, the volume over which you can detect the gravitational waves goes like the third power. So just by increasing the distance by a factor of 2, you can see 8 times as many of these events, which is really exciting.
But the light gets a lot fainter.
Yeah, it's harder to
So
do.
it's much harder.
And another,
Yeah.
and then also if it's for the further away events, that means that there's also, you're probing a larger volume, which is good for finding more of these, but that also means there's more false positives. Yeah. So normal supernovae are much more likely. So if you find something much farther away, if you find a counterpart, you have to be more worried that it's just a normal supernova that has happened to be in the same location and unrelated to the gravitational waves.
Your question over here.
Yeah, hello. First, let me start by I'm going to ask about gravitational waves, the concept of them. I start by even questioning time and space. I mean, quite frankly, they may just be characteristics of matter, and if that's so, the matter, as we understand it, is a very small portion of everything anyway. So but set that aside. My real question about gravitational waves, if there are these depressions, so to speak, first of all, it would seem to me they'd be overlapping, like counter waves coming from all kinds of different directions. Yeah. And in addition to that, so the whole movement of the universe, therefore, would be kind of wiggling around like that, hitting those different waves. And also, the last part was, can you detect, or it seems you would be able to detect, sort of the effect, the drag, so to speak, on something going around another thing. The drag itself would have an effect, say, on the moon or something like that. So if that's the case, it would seem things would kind of collapse a lot. But
so those are all really good points. So you're definitely right that if you're sitting here detecting gravitational waves. There could be gravitational waves coming from multiple sources at the same time. But it's just like when we hear. If I have different people talking around me, I can detect the waves from multiple people talking at the same time, and I can still hear multiple different conversations at the same time. And that's actually a worry with this LISA detector I was mentioning before, where you have it in space, and you'd be able to detect things much further away with this much more sensitive gravitational wave detector. They're actually expecting to hear multiple different things merging at the same time, and then they'll have to piece together, okay, there was this guy here and this one here, all happening at the same time.
Would you get drag out of that? Would you get
So that's the last thing that's interesting is there is actually an effect called frame dragging. When you have massive objects like the neutron stars spinning around, they can actually drag space-time around with them. And we see effects like that, for example, when light comes from neutron stars directly, and we see like X-rays coming from them, you actually see different parts of the back end of the neutron star from the space being so bent as the light's passing away from it. So thank you.
Thank you.
Yeah, and with the background aspect of it, I just wanted to add on that there are actually other types of detectors that aren't physical things, but there are collaborations trying to use large numbers of actually neutron stars in space that are spinning quickly to detect a gravitational wave background. So actually detect sort of the rumbling or, like the background noise if you were in a crowded room. They're trying to detect that. But even on top of that, if somebody, you could detect the background noise. If somebody then shouts in your ear, you're going to be able to hear both. So.
Right over here.
I assume by now the neutron stars have gone dark. And my question is, having measured all the ejecta and calculated the masses of the heavy elements and so on, what does astrophysics predict would be left in the core where those two had collided?
So that's a great question. So when you merge two neutron stars, you lose some of the mass as you throw it out. You also lose some of the mass just because you become more bound. But you're still left with more mass than either of the individual neutron stars. So then it depends on the exact equation of state, which is how stiff neutron stars are, if they can then support that amount of material and stay a neutron star or collapse into a black hole. On either one, if they collapse into a black hole, they should then ring down, which means when it collapses, it still wobbles around a little bit and emits more gravitational waves. Unfortunately, from this source, they looked and they didn't see any signatures that they would expect from ring down, but it wasn't quite constraining enough for this individual source to put interesting limits on that.
Yeah, so I guess in summary, it could either be a neutron star or a black hole, depending exactly how much mass there was. It was a big debate with this object for a while, what it was. Eventually, LIGO will be able to, on its own, tell the difference once its sensitivity gets better. With this object, then there's a lot of debate, because there's other ways with the light you can try and disentangle. For instance, we do know that there was a Gammaray burst now, and some people studying the properties of that jet can tell you that there are differences in what you would see, whether if there was a black hole afterwards, or even what exactly type of material was created. How many heavy elements were there? Were they light heavy elements or heavy elements? And if you start to piece together multiple mergers, you can start to use that to also tell whether black holes or neutron stars were formed. I think right now the best thought is it was a black hole. I don't know if Tony.
Yeah, so I was actually just calculating some of this last week, trying to think about it. And the conclusion, it looks like, the thing to add is this material that neutron stars are made out of is so exotic, like I was describing earlier, that we can't really do experiments on Earth to actually study things like this, because it's basically like a giant atom that has the mass greater than our sun. And so these objects are one of the best ways we have to actually study this type of matter. And eventually, LIGO will be able to tell us afterwards whether it was a neutron star or black hole that was generated once it's more sensitive at higher frequencies. But my expectation, given what we know about this dense matter, is you probably had a neutron star for a little while that was kind of massive, and it was differentially rotating, and then eventually it collapsed over its own weight and eventually produced a black hole. And part of the evidence for that is we don't see any X-rays or additional emission coming out of it now, besides the jet, which is actually still producing radio waves that we're still detecting, even now, a year later. But we don't see any X-rays coming from that neutron star, so I don't believe there's a surface left there anymore.
Hi. So if I recall correctly, scientists were originally surprised by like the X-ray and the radio waves they got from the merger. I think it was like the X-rays were kind of late and of low intensity. I remember some people were saying that was because of the direction of the relativistic jets, but other people were claiming that like our theory of how the merger happened was wrong. So which one did it turn out to be?
Excellent question.
So yeah, so you're exactly right. So what happened is the X-rays turn on about a week later,
Yeah.
and then the radios a little while after that. And what we believe happened is, what happens is the neutron stars merge, and somehow it drives a relativistic jet with an opening angle around 10 degrees or so, jetted away. We see these as what we call Gammaray bursts, but when we see these things, they're always beamed right toward us, right? But now, because of gravitational waves, we were able to find one that wasn't necessarily shooting right at us. And so not surprisingly, given the small beaming angle, you could actually see that they were beamed away from us. And this has been confirmed by radio detection. So by actually combining giant radio detectors across the Earth, you can actually see the size of the jet that's moving away. And you can actually tell that it's moving away from the neutron star merger site. So we can actually find this jet now and see that was the explanation, that it was just a jet that was beamed away from us that caused this.
So yeah, it was debated for a while, even when the initial radio and X-ray observations happened, exactly as you said, was it that this jet was just pointed away from us, or was it something actually different than the gamma ray burst we had seen previously, something more spherical but still high energy? And now, as over time, both the X-rays and radios have started to fade, and we have actually seen sort of the size of it now, most of the models are going towards it was a jet, just pointed away from us.
Good question.
This event was detected last August. When did these two neutron stars actually collide? How long ago did that happen?
So it was about 130 million years ago, plus or minus a little bit. And that's just from the distance to this galaxy is 130 million light years away. And so that's one of the really cool things about this object, actually, is you can actually, because the gravitational waves and the light came at almost the same time, even though they're that far away, you can actually use this, for example, to measure the speed of the gravitational waves and show that they're almost exactly the speed of light, which is a really important confirmation of Einstein's theory of general relativity.
Hi. I guess I was just very curious to know for each one of you how kind of being a part of this observation and analysis and being able to ponder this now for about a year and work with the people in your field about it, how has this impacted you personally? You know, what's been the most exciting thing, and also has it changed the way you think about anything, be it in your field or just in the universe?
So a reporter actually asked me about this this event. She's like, "Oh, what is it like to be part of a once-in-a-lifetime discovery?" And my response was, well, I hope this isn't the only one in my lifetime. So I think this was a very big result that's very exciting, and it's great to be able to like stretch our knowledge. But so much is happening right now in transient astronomy, which are discovering things that change, like supernovae and the kilonova, and gravitational wave astronomy, that basically, the thing looking back on this I take away is that I think the next 5-10 years are incredibly exciting. I think we're going to have many surprises from nature, because this isn't my quote, but it turns out that nature is typically more creative than we are. So things that we imagine that we're going to find, nature, we sometimes find those, like this we imagined, but often nature just completely surprises us and throws a curveball, and we see it, and then we're scrambling to try to figure out what it was. So I think that's kind of my takeaway and kind of looking forward.
Well, I mean, I got a job, so that's good. I mean, that's mostly a job. I'd like to think that would have happened anyway. So, but it is true that I now have a new job as a faculty member, at least probably in part because of this. But no, I think I would look back and more think about how it impacted me at the time as well, because it's something that we do astronomy research all the time, and we study these amazing things, explosions in space, but it's something that our day-to-day lives can be quite mundane sometimes. It's like, actually, I'm sending emails and I'm fighting with code on my computer. And this is one of the reasons I still really love traveling down to telescopes. A lot more of it has become robotic, and that's very good in terms of efficiency in science. But I still love going to the mountain because you actually see the data come in, and it's just a reminder at how amazing and mind-blowing and beautiful the universe is and what we're actually studying. And I would say for me, I definitely had a moment like that first night when that first image came in, and it was just even sent around via email and being like, I found something. Like, that was the only contents of the email, but it was the image, and you could see the new source, and it just was slightly offset from the galaxy, and it's like, we didn't even know it was for sure the thing at the time, but it was just sort of like, my breath did stop for a minute, and it just reminds you how amazing the universe actually is and how fortunate we are to be able to do this for a career.
Yeah, unlike Tony, when Charlie sent around that email, all he said was, I think I found something, period. No exclamation point.
Yeah, exactly.
Just
like, I think I found something. Yeah.
Yeah. I just think back to it, and it was just such an exciting time then when there was new data coming in every day, and we'd reanalyze it and calculate velocities for how the material was expanding and seeing how the colors were changing, and just waiting for that data each day was so exciting. But it was also very stressful where we had to have, I talked about these 10 papers that we had to have finished. So we took like 3 weeks putting the data together, and then we had to analyze it and write all these papers by October because LIGO had set a date that everyone was going to release their findings at the same time. And so we had this set date where we knew we had to finish by. And so I looked back and I was like, oh my gosh, how did we get through all of that? It was like incredible that it worked out. But like Ben was saying, I really feel like it's just the start of something now where there's going to be more of these types of events. They're going to show more diversity. They're going to probably keep surprising us. And so as a theorist, I'm happy to now walk away from the telescopes a little bit, go back to my pencil and paper, and work out some theories to start describing the next series of events that we're going to be discovering.
To give it a little more human angle, so Tony was saying it was very stressful and time consuming to do this. So we went on this trip around Utah, but a week after the gravitational wave source, I moved. All my stuff was packed up. And then I had a trip planned to go and give talks to different people. So then I went to Ohio, Princeton, Cambridge, UK, Berlin, Italy.
This was during his homeless period before starting a new job.
And then during this time, we're still getting data and still reducing it. So I think I probably slept, I don't know, probably an average of like 3 hours per night for over a month.
This is not a good place to end this, Ben.
So I know a little bit about these two folks here. At the time, we're both applying for jobs, somewhat. And I was one of Maria's letter writers. And of course, this event had happened, but I couldn't say the event had happened. And so I just wrote an email to the director of the department, the chair of the department at Toronto, who I know very well. And I just said, look, you just better hire her because in about another month, you're not going to be able to. And the remarkable thing is she actually didn't even have to give a job talk, which I don't know if that's, I don't, I mean, they knew her. She had spent time there. And so this was not a one-off hire in some sense, but I mean, I just think it was pretty remarkable that was the power of a single email. Yeah. In the case of Tony, I was trying to make a case to our president that Tony should be promoted to be a staff member, so the timing really could not have been better. It made the case pretty easy. We have another question here.
Very basic. I hope you'll forgive me. Discovery of gravitational waves in 2015, you said at the beginning of your talk. Could you remind us what that discovery confirmed about general relativity, our understanding for how that describes the universe and how our understanding of that changed once gravitational waves were detected and confirmed?
I mean, this was an important confirmation of Einstein's theory of general relativity. So in the past, we had detected gravitational waves, but it's always indirectly. And the most famous one is what's called the Hulse-Taylor pulsar. These are two neutron stars in our own galaxy that we see rotating, revolving around each other, getting closer and closer together. And the way they're coming together exactly matches Einstein's prediction of general relativity. And in fact, the discoverers of this binary won the Nobel Prize. and the early 90s for this discovery, but this is indirect, right? You're seeing something changing. It fits with gravitational waves, but you haven't actually detected those gravitational waves directly.
So maybe it's something else that no one's thought of yet.
Yeah, so this, in the case of the black holes merging, this was actually, those the gravitational waves were hitting our detectors. We were actually detecting them exactly how Einstein predicted it.
May I follow up very briefly? Waves, to me, mean surfing. I would like to imagine a speculative future where the energy of these waves could be somehow harnessed and you could use them to transport yourself extremely large distances. Surf them. I want to surf them.
So here on Earth, right, so we measure this with LIGO, which is 4 kilometers long, but the change that they're measuring, even for this, nearby strong signature, is significantly less than the width of a proton. So I think you might have a really small surfboard.
Yeah. Great answer, yeah. We're gonna do one more question over here on the.
So you actually just mentioned the orbiting pulsar binary, which is very exciting because you can ask a lot of nice questions about it. But if the next merger was a pair of pulsars, what kinds of questions could we be answering? Or would it just be the same questions we were already answering with that pulsar orbit?
So the expectation is that these neutron stars that merge probably were pulsars, in fact. It's just that the pulsars, if you guys don't know, they're basically neutron stars, and they have, because they're so dense, they're able to hold very strong magnetic fields. And the particles moving along those magnetic fields produce radio waves that we see in our galaxy. And what happens is, as the pulsar spins by, you see that pole coming in and out of your line of sight, and this is what we call the pulsars. Okay, these things are incredible clocks because they're just so dense. They're like they're more exact than even some atomic clocks. And so it's expected that these neutron stars that merged that we detected probably were pulsars. It's just the problem is they're too far away when they're in other galaxies. We can't detect those radio waves in those cases yet. So it was a good question.
All righty, I want to just remind everybody that our next Capital Evening Lecture is on October 3rd. It's Carla Schultz. This is one of our Kavli lectures, so this should be really very exciting. So we hope we'll see you all then. I want to just take a minute, since I have a chance to we should congratulate these individuals just for this really amazing work that they did. Yeah, you got a standing ovation, look. Yeah. It's the one thing we didn't emphasize about this. Of course, there's an element of luck being in the right place at the right time, but they really had the observing strategy that beat all the other observing strategies. I mean, I think that really is something that should be quantified. So we want to thank you for that. We want to thank you for coming to this.